Well, hello everyone, and welcome to part 15 of my DLL injection into all processes tutorial. Today, hopefully we will be finalizing our shellcode and invoking shellcode and also loading of our FAKE.DLL. So without any delays, let's go back to our development environment and let's load our InjectDLL, and that's the name of our solution. Now, if you remember, we left off last time on mapping our shellcode or our section for the shellcode. And again, now let me bring back this diagram here. And remember, I showed you that we will be mapping kind of like our shellcode here so that it doesn't go at the preferred address. And then I said the shellcode will map the same section again over here. Now, the question that kind of like popped in my mind after I recorded it is, how is it possible that FAKE.DLL will be mapped twice? Because, obviously you can't load DLL twice, the loader won't let you. Well, the reason being is that we are not mapping it. Let me just show you real quick. If we go here, we're not mapping it using the usual loader load library or whatever, mapping of the DLL. We just map it as a section. And we can map it as many times as we want. It's just that we mapped it for execution. And obviously, if we did this with our shellcode and tried to run any code that needed relocation and snapping, like I was explaining here, it would not run. And the only reason we can run our shellcode here is because it is base independent. So if you go a few modules back, I think it was 12, maybe 13, part 12 or 13, can't remember right now, but you can look it up. We wrote this whole assembly stuff, and the reason we did this in assembly is so that we can do it base independent. In other words, there is no snapping that needed here. This code, you can put it anywhere you want and it will run. All it needs, it needs like these two parameters, which is the base address of our own module here and also the DLL name that we are injecting, and that will resolve loader load DLL, call it with this DLL, so load it, and eventually it will unmap the section that this code runs in, or in other words, it will unmap this here, the shellcode. And also, if we go back to the map section for shellcode, I put this comment here that once we return success, we need to unmap this section. And I put, this API here, but it doesn't have to be this specific API. That can be pretty much any API that unmaps view of section. And the reason we need to do this, obviously, is because we mapped it here. And if we look at our shellcode, this is exactly what it does. Right at the end here, remember we did jump, and we actually put this comment here. And the reason, again, if you remember, we did this via a jump. We invoked this unmap view of section, the API, from within the section itself, is so that it can unmap itself. And while it was unmapping itself, obviously we can't use call, because if the execution came back after the section is unmapped, well, we will get some undefined behavior, because there might be something else here at the time. So basically, what we're doing is that this function, when it gets invoked, this will map our section here. Then we will need to, let's see where this function is called. So I'm going to use global search. And let's see, it is invoked. Let's see, come on, it's invoked right here. So basically, once we get this, once we get success, we can, on the next step, we can actually run our shellcode or run this procedure that will inject our FAKE.DLL that we pass into it, and will also unmap itself. So this is kind of like the goal here that we are trying to achieve. Okay, so that is the recap of what we, what we were prepping up before. And right now, what I want to do, I need to explain a little bit this whole, APC game that I'm doing here. Now, and for that, the easiest way would probably be to refer back to my drawing here. And I'm sorry I have to subject you to that again. Okay, now before we do, if you remember a few modules back, I explained this whole kernel routine, normal routine, and rundown routine. Now the rundown routine is not very interesting in our case because it's kind of like a default, not default, but kind of like a fallback type situation when the APC doesn't get queued and the thread gets chewed up or closed or terminated before APC actually has a chance to run. But what is interesting for us is the kernel routine and the normal routine. As always, the kernel routine runs first. It usually runs as an interrupt, so it happens almost right away. And the normal routine runs depending on the settings with which you invoke the API. So just to understand what I'm trying to do, I'm going to use some drawing. Okay, so if I do it like so. Okay, guys, so if we imagine, let's see, I'm going to do some unconventional here, and I'm going to divide the screen in two, and I'm going to say that the kernel mode stuff will go on the left, and the user mode will go on the right. Okay, so anything happening in the kernel will be on the left, and the user mode is here. So then let me switch, to blue. And if you remember, let's go back to the source code, and in our DLL main, we have this OnLoadImage, which is a callback that happens when we get our DLL injected, when our DLL is mapped, not our DLL, when kernel 32 is mapped, and that's when we will want to map our own DLL. So let me put it right here. So first we have on load image, and let me put it like so. It's a callback, and what is important, let me put it with the asterisk, is that it is called from under a critical section. I'm going to abbreviate it as a log. So in other words, this onLoadImage happens from within this very specific and special, special area of the kernel that's called from log. That is why we are invoking an APC, right? So the reason to not lock up the system is not to do all the work within this critical section, but instead to delay it, and that's the A in APC, which means asynchronous. And what usually happens, like inside of these kind of critical sections or locks, is that APCs are disabled, so you can't really invoke them. But very shortly, when you come out from that lock, the APCs are allowed back, and the first thing we get here is that our kernel routine gets invoked, right? Guys, I'm sorry, I'm just drawing with this thing. I'm so bad. Okay, now kernel routine, if you remember, if we go back to our moment when we invoked the APC, so let me just use search for kind of quicker access. And let's see, right here, when we initialized the APC, when we specified the kernel mode. So this callback, let me just like abbreviate it to mode, will run in a kernel mode. Now if you also remember, it will be running at APC url. Now this means that it's not very convenient for us to be doing a lot of things here in the kernel routine, so we don't really do much. And what we do, we simply defer all the work to a normal routine, and that's the second routine or the callback that will be called And this one, it will be called at passive URL, which means that we can do stuff here. And the mode is, again, kernel, because obviously I am on the left-hand side, so I'm in the kernel section. So right now, that's where we can do most of our work. But again, if you look at our let's see, at our normal routine, we actually call, you see we are in a normal routine, and we actually call our mapping of the shellcode from the normal routine. Okay? But if you remember, our goal actually is to be in the user mode, and that is why we will queue another APC. Let me do in green, I guess. We will queue another APC. Now this one, it will be user mode, and the old one, let me just put it right here, it was kernel mode. So, and that's the difference. So then we will queue the second APC, and we will again get our kernel routine. Well, the reason it's called kernel is that it actually executes in the kernel, and again it will be running at APC URL, but the mode will be user. Now what this tells us, and the reason for the kernel routine, is so that we can actually adjust what is being passed into the normal routine. And in this case we really don't do anything. But the interesting thing, because it's a user mode routine, the normal routine would actually run in a user mode. So let me just write it right here. And that's where we get our user routine. And obviously the mode here is user, because we are on the right. And this is the callback where we would have our shellcode. So if you remember our diagram here, you see this shellcode here or here, this is where we are. So if I go back to black, kind of try to draw it as such, this here is our FAKE.DLL, right? Which is not exactly FAKE.DLL, it's mapped section that is taken from FAKE.DLL, but that's basically what it is. And this normal routine would be our shellcode. This thing here would be this user mode normal routine. And let me see if I can write it down. User mode normal routine. Well, that was a bad idea, but this code here is basically this assembly code in this routine that will run in our user mode. Okay, and this code will be mapping our DLL main at the preferred address like I described over there. So guys, this is kind of like an outline in my chicken scratch drawing of what we are doing, and basically the APC play that is going on here. So let's look into code and let's tidy up what we're actually doing here. So let's go to the beginning and into our InjectDLL, and as you can see, we allocated some space for KAPC structure, and let's see if we actually manage it correctly. So we set up all the routines here, and we incremented our driver reference to driver object and also to our section to make sure that they're not unloaded, and we inserted APC into the queue. At this point, the callback, the kernel callback, will probably start executing even before we return from here. So at this point, we just return success. And actually, you know what? No, it won't. We will have to come out from the callback from onload, but it will happen almost instantaneously. Now, if we fail, we obviously have to dereference both things that we did here and also remove the memory from the allocation. Now, the rundown routine at this point will not happen right away because we are in the kernel and we are specifying kernel mode and current thread, so it's already running, so the system thread will not terminate. So this rundown would not happen for us in this case, and instead we get kernel routine. In the kernel routine, we check if we are in the kernel mode, and in this case we are, and we are not dereferencing our driver. So then we get to the normal routine, and because the APC was kernel, we are also running in the kernel here. We will map our shellcode. We will get our section, and as soon as we get a section, we can dereference it. In other words, we can decrement that reference to section that we did before we queued APC. And let's see what happens if we fail. Well, if we fail, we write a message here, but what we also need to do, we need to deallocate our KAPC structure here, which we haven't done, so let's do it now. Let's just say free mem, and we're using X. Oh, come on, this is so ridiculous. I need to change this. Every time in the Visual Studio they try to be helpful with this bullshit, but it is not. Sorry guys. Okay, so we remove APC and memory for the MPC, for the APC for the asynchronous procedure call, and we dereference our driver. So in this case, we get here in case of an error, or if we don't continue with our chain. And our chain is here, so we're in the normal routine. Okay, guys, so let's see, let's get here in case our shellcode was actually mapped. So if it is mapped, we need to queue these two APCs. We need to do kernel routine, which is again is just the way things work in Windows. So first is kernel routine, and then is our normal routine. So let's do that, and we would do again key KE initialize APC, and again we pass the pointer. We set the get current thread. Let's see, get current thread. Okay, so we pretty much do the same thing. I should have just done copy and paste. So we do original APC environment, and we will reuse our kernel routine. And again, we're using rundown routine. And the third one would be the actual normal routine in the user mode, which we don't have yet. We'll calculate it later. Let's see, what else do we need? We need APC mode. This is important. This time it's a user mode. And the last one is the normal context that will be passed into the normal routine, and we don't know it yet, right? So let's put our comments, and let's say set up user mode APC that will do the injection for us. And you know what, let me just search out the previous declaration, and I'm just going to copy this stuff because I don't want to type it again. So let's see, it was where the routines were. Again, just a comment here. And which is important here, we need to say that this is user mode APC. And this is the pass. Now if we look, okay, let's set up our user mode routine. In the user mode routine, as you see, we have this normal context, so we need to pass a base address into it. So if we go back and let's say pass base address as context into normal routine, and let's see, our base address is this. That's what we get from mapping our section. Okay, and the last thing that we need to do, well, not last, but we need to make sure that we have this base address. Again, just a little sanity check here. And we need to get this address from our mapped section. Well, let's just calculate. We pretty much have everything already. Let's just say define our user mode normal routine, which is, no, this is not it. This is it. Function. Okay, and what we do, let's just do pk normal routine, and we're just going to say p user mode normal routine, and obviously we'll have to do some casting here. And let's see, how do we calculate it? Well, first of all, we take our base address and we need to cast it into byte pointer so we can add an offset to it. And the offset we take from our DLL stats, and if you remember, we calculated this RVA to our shellcode. And since we're using it here, let's just put an assertion right above to make sure that we actually got it. Again, just a little sanity check here. And that's pretty much, you know, everything we need to do here, because again, remember we had this shellcode offset that we calculated when we were mapping, when we were creating our section. And we just need to add it to the base address. So, and that's pretty much all we have here. So let's add it as a kernel routine, and that will set up our kernel normal routine for the user mode APC. And let's see, so that will do. Now there's a little bit of work that we need to do for WoW 64 section. Let's see, section only, and let's see, let me just put need more work here. Okay, so that basically means that for the 32-bit section we need to add a little bit of a work before we can actually, you know, invoke this routine as such, but we'll get to it later. Because right now we're not at this point. We just need to get kind of like the most important stuff done. Let's see, and also if you see over here, we also have the system parameter that is InjectDLL name that we need to pass. And if you remember, it was also stored here in our DLL stats structure that we calculated already. So we need to pretty much calculate pointer to the injected DLL name in, let's see, name, come on, in user mode address space. Okay, so let's see, let's just put another comment here. Such DLL must be placed in the system32 folder of the appropriateness. Okay, so again, it just basically says that, hey, you can't just take any name. We have to like pick specific name. And let's see, p void, I guess p, let's use the same naming convention, UserModeDLL name. And we'll definitely have to cast it probably to p void. And let's see, you know what, it's exact same thing here, actually this thing here, except that we will be using our VA for DLL name, because again, we have all this information. The only thing we need to do is do a sanity check as such. Okay, now how do we pass this system argument? Well, if you remember in our previous example here, when we initialize APC, we can actually pass them right here. So let's do the same. But before we do that, we have to prevent our driver from unloading. So let's just write it down, write it out. Since we are queuing another APC. Okay, and what we do is object reference object, and we provide the driver name. Let's see, I think it's driver object. Again, because we're queuing APC, we have to do this so that the driver doesn't get unloaded in the meantime. And we have to handle errors. Okay, so here, this is very similar to what we did before, except that here we will have pointer to our InjectDLL name as constant wchar and null terminated. Okay, so we do not use system parameter 2. We only pass the DLL name. And this argument will be passed into our routine here as a second parameter, and that's pretty much what we wanted. Okay, so over here we can say that we queued APC OK. And before we get to it, let's handle the error. And the error probably get handled the same way as we did here. Let me just kind of copy and paste this, so I don't want to just type it up more than once. Okay, so the status will be bad data. It will tell the calling function or whatever that we need to do here that basically there's a problem. And let's see, we need to say that normal routine. Just trying to provide some helpful debugging output here. Insert QAPC failed, and then we have process ID and context, and the context actually comes, let's see, where is our struct here? I'm sorry, and the section type comes from over here. Okay, so this will be an error message, but before we get here, we actually have to dereference our driver. Let's just say reverse reference count, and what we're doing is object dereference object, specify our driver. And if you remember, when we got here, we got this message that we need to unmap our section. Well, because we failed to queue an APC for some reason, we need to unmap our section. Let's see, and unmap. And let's see, unmap section with Shellcode. And in this case, we can use that internal API, which I did not define yet. So let me go fetch that. So guys, I'm just using copy and paste here from my solution. From my own cheat sheet into this solution. And this is very simple, takes the process and base address. So let's go back and let's see. So we get IO get current process. And again, the reason we call IO type function is because we need PE process here for this API. And the base address is the base address that we got from the original function. Okay, and right here, let's just kind of do a sanity check again to make sure that we have the base address. And let's see, because it returns NT status, I'm going to do my verify NT success macros here, again, just to make sure that nothing fails. Okay, and then when we get here, we also need to free our APC memory and dereference our driver again from our original APC. Okay, so this way we will handle an error, so we won't be hanging any of our driver or memory that we allocated or sections. Okay, now let's deal with what happens when we actually queued an APC. Well, at this point, we do not need to get here to free the memory. Instead, we can just call return from over here. Now, we will return true to dereference our driver object, because again, the driver object was referenced here. If you remember when we queued APC for the kernel mode, so we need to dereference it, because we did another referencing here, so we did it kind of twice, but we are undoing one from the previous call. And last thing, well, just to speed things up, we need to force, let's see, force the call to the user mode APC. Now at this point, guys, we can actually have our rundown routine called, and in this case, the rundown routine will clean out our memory and will dereference our driver. So that's what we pretty much had here. And to force, well, the way this works, by the way, is that when we queue this user mode APC, the kernel routine will be called exact same way, but the user mode APC routine will not be called until the execution transfers back into user mode, usually through some system call or the context switch. But that's at this point, as soon as the CPU transitions into the user mode, the normal routine will be called. Well, we can actually, instead of waiting for it, we can force it. And there's an API which is undocumented called test alert thread. And because it's undocumented, I have to go and bring that declaration for you. And I'm going to put it right here into our driver types. Okay, so what it takes basically is the alert mode, and what we need to tell it is to use user mode. Very, very simple, doesn't really take many parameters. And then we'll just force that transition, we'll basically force the call. And we need this because, again, of the way user mode APIs are executed. And let's just say it will, let's see, the APC will be handled. I'm just going to put what I just explained to you in words by the user mode function in the DLL asm64.asm or DLL asm32.asm files. Okay, and that's how we would transition into our user mode normal routine written in assembly. Now, before we go any further, we need to take care of this kernel routine that will be running again. If you remember, we specified kernel routine, but we didn't check the code for it. So here's our kernel routine procedure. And in this case, when we get here, the mode will be user mode. We don't really need to do much. The only thing we need to do, we need to free our APC memory, kind of what we did right here. And the reason we are doing it is because if you look here, we will not get back to the kernel mode, and we can't free it from the user mode from a normal routine like we did otherwise. So this is important for us to do. Let's do it as such. And let's clean out spaces here. And that's pretty much all we need to do from the kernel routine. And that will basically conclude, I think, it will conclude except for this little work that we need to do for WoW64. That will conclude our queuing of the APC or all this stuff here. So let's make sure that our driver actually builds. And it does. Let's make sure that it builds for both 64 and 32. Okay, and let's also test release. I usually do for all four just to make sure that I did not introduce something, unusual that I wasn't expecting before. Oops. Release and x64. Now release would be our production release of our driver, and it will not have any any debugging output, none of the stuff none of the debug prints like these stuff you see. Okay, but testing will be done in a debug mode, and as you can see, we are pretty much done with queuing of our APC. Okay, well, the thing that we have left is actually to call all of the stuff that we've been doing here. Because if you remember right here, we have our get section, and again, this is the onload callback. So the get section is a singleton that will create our section as a known DLL the first time, and then any consecutive times it will just return us a pointer to our structure that will contain all the information that we need. So the next thing to do is we need to put our function that we just wrote that will inject everything. I like these finishing touches when you actually kind of like put everything together, when you like wrote like some very long function and then you just have to call it. That's like really cool. Okay, so we call InjectDLL, and we have to provide our DLL stats, which we got from up above, and obviously it will give us status. And what we need to do is we need to see if we failed, and failed would be opposite to success, obviously. So that would be it, and then we can say there is an error, and we can output that error in the debugging view, in the debugging console. And I'm gonna say section InjectDLL PID, so that's pretty much all we can do here. And yeah, so pretty much inject will inject and run our code, so it doesn't really, we don't really have to do anything else. The only thing we need to do is actually provide the same thing for our wow section. And if you remember, the first time I did this code, I did not change this to this, and that was pretty stupid. So let me do that. Let me change this. And guys, I think over here we are kind of done, right? This is really simple. We're just like inject and do the same here as well. Okay, well, let's try building it. And our driver has been built. So then, we haven't really tested it for a while in our test environment. So I think we are at the point when we can actually do the testing. If you look into our get section here, oh no, I'm sorry, not get section. We were right here where we needed to be. We actually have this limit injection to proc, and we are limiting to notepad. So what our driver will be doing, it will be limiting it only to notepad. So it means we can actually test it on the live system and see how, if we can inject our FAKE.DLL into notepad. So for that, we built our our driver right here, and we built it as debug, because again, debug will have all of our debugging output, and we have verbose also uncommented, so we need to see all the verbose output. But now we need to actually build release builds of our FAKE.DLL. And the reason we do release is because, well, this is very shortened down, cuts, pared down DLL with only certain imports. I'm sorry, certain exports. So let's rebuild both 32 and 64-bit versions. And before I actually bring them into the test environment, let me make sure that we have everything built correctly. So if we take our driver, we can see what's going on internally. And again, we have imports from NT kernel OS. That's pretty much what we need. These are basically all the functions that we were using. Okay, that worked. Now let's see FAKE.DLL. Let's see all imports. And we have a little bit of a problem here. Oh, I'm sorry, guys. I'm taking the wrong one. You see, this is important because I took it from debug. Let's see what happens. I'm just going to show you the wrong one. See, it's not just NT.DLL. We have Visual C runtime. There's a whole bunch of other things. Kernel, yes, so this is definitely not the one we need. We need the one from release. And by the way, not this one, but this one for 64-bit. So if we take this one and check, you see the difference? This one has only imports from NT.DLL, and it has 2 exports. This one is the one where we keep our shellcode, normal routine, UserModeNormalRoutine, written in assembly. Remember, like, we exported it as ordinal at number 1 so that we can look it up faster. And this one is our little fake function to put static variables, and also to bypass, not to bypass, but to provide compatibility with control flow guard. So just look a couple modules back and you'll see what I mean. Okay, and let's do the same and check our FAKE.DLL. Ideally, it should have the same output, and it does. Okay, guys, now this is kind of tricky. So, I mean, not tricky, but we need to pick the right ones. So again, debug for the driver. We take driver64.sys. Let's copy it, and let's go into our test environment and paste it here. It's a much larger driver now, so let's take it here. And before we start it, we need to bring in both DLLs. Again, we don't take it from this folder, we take it from release. And again, let's just do real quick before we copy. Okay, that's the right one. So I'm going to copy it. I'm doing one at a time. I'm going to copy it on the desktop because of the way virtual machines basically they don't like when I copy it directly for some reason into Windows System 32. Now I'm going to System 32 because we are in a 64-bit environment. Come on, what's going on? Did it hang up? Some reason, yeah, the virtual machine hung up. Okay, so we move here, replace existing, continue, and it wants me to provide my admin credentials. So here you go. This is System 32. And then let's go back, and in this case we need release and FAKE.DLL 32. Again, let's check it with WinAPI search, and this is correct. Let's copy it. Again, go back to our test environment, and in this case it's a 32-bit DLL, so we have to go to System wow64 and well, now let's do paste to the desktop and then copy it here and move it there. Let's see, replace existing, continue, provide my credentials, and here we go. Okay, well, this is the moment of truth, so let's clear the debug view and let's register and start a driver. Okay, so here you go, and let me start Notepad. And as you can see, we didn't get any errors, and we actually mapped into a process. Interesting. Well, let's see if we run process hacker and go down and find Notepad, go into its properties and look up the name of DLLs. FAKE.DLL 64 is actually injected into it. You see test DLL inject to inject in all processes. So here you go. We have it actually running into our 64-bit DLL. That is really cool. Now, technically, if we run the same Notepad again, it should not create a known DLL, but it should inject into it. And here you go. It did not create. You see there's only map that gives us kernel routines. By the way, we can see that like from over here, we have our image load, wow0, which means 64-bit process. And it's 5864 process ID. And let's look it up. Yep, here we go, 5864 in process hacker. Then we had kernel routine, which was executing at url1, which is APC. And then we got normal routine at passive level, which is correct. The mode is 0, which is kernel, and we have APC structure, which is again allocated from kernel space, which is also correct. And the section type is N for native, so far so good. Okay, well, let's see. We also have, and that's when the shellcode was mapped. And we have this error message, which is not error, which is warning, which is correct. And let's look it up, what it means. So if we do this, WinAPI search and go into error search, and just scoot it over like so. And then if we search for 0x, I'm just taking this thing, 4000003, I think. Let's search, and what we need is NTDLL, and let's see, here you go. Let me stop this. An image file could not be mapped at the address specified in the image. Local fixup must be performed on the image. So this basically exactly what happened in this diagram as I was describing for you. Remember, like a few modules back right here, when we placed our memory. Let me just show you real quick in the code so you can actually see. So I have to switch back to our development environment. If you go into our section here, into map section for shellcode, remember we allocated memory at the preferred address, and then we invoked map view of section at the basically to map the section. Well, it was this situation when we were calling it from, when we put some bogus basically memory here, and we wanted to map our DLL. Well, it didn't use the preferred address. And that's exactly what this error message means. So this 4000 blah 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 3 is what we needed. Okay, and then we got our kernel routine that executed the second time, and url1, which is APC, mode is 1. And what we are looking at is basically this here, and mode 1 means user mode. Okay, and the next time we actually got into our DLL here, and I'm sorry, into our notepad, and that executed our DLL main. And look at this, we got our DLL, our log file. So if we open it up, it actually gives us the time that we ran, and again it's May 24th today at 11:41, and that's exactly the time that I ran it the first time. And interestingly, because I opened another notepad to browse this file, to open this file, you see it injected one more time, as you can see here. So at this point, we can tell that our 64-bit injection is working. And just for the heck of it, guys, let me show you what happens if I try to run a 32-bit version of Notepad. As you can see, nothing happens. We get a crash. And I haven't had any crashes yet. You know, even though we don't see anything here, it seems like everything was fine. If you remember, originally I was using my WERSetup to get the crash dumps. So if we do go into the crash dump folder, we get actually a crash dump for Notepad, which just happened. If you look at the time, again, this is today, 11:46 a.m. That's the time now. And I can probably show you right here. You see 11:47. And if we switch back, this is how you catch crashes. So in my case, I didn't have to deal with crashes because, you know, obviously I was, I knew what I was doing at this point, so I avoided them. But when I was developing everything, I had quite a few crashes. So this is how you can catch a crash. And then the way you deal with it, you basically take it to your development environment and you analyze it. You open it in Visual Studio and see where the crash came from. Now, I'm not going to complicate this video with the crash dump analysis because it's a totally different ball game. But just to show you how you can collect crashes from the system. And the way you can see that something is crashed is that, remember when I double-clicked on, let's see, where is it? On Notepad here, it didn't start. So, and that's how you can tell that something crashed. Okay, so I'm just going to delete it since I don't need it. Okay, well, guys, at this point, we need to modify our driver so that we can inject into 32-bit processes. But before we do this, we need to stop it to make sure that it doesn't mess anything up here. So let's go back to our development environment, and if we look into inject, no, I'm sorry, not inject, we need a normal routine. And in the normal routine, where we, you know, before we use the normal routine address, I left this out, basically saying that, hey, we need to modify it for WoW64 section. So let's do it right now. And well, first of all, we don't really need to do this if we're not building a 64-bit version of our driver. By the way, we haven't even come to testing to our 32-bit driver, so we'll probably do it next time. But in this case, we don't need to do it, so let's switch back to 64-bit version here. Okay, and first we need to see what kind of a section we are dealing with. And remember, the section type is in our DLL stats, and it's a section type. And let's see, I already forgot how I named them. Okay, so if we are using this section WoW, which is 32-bit on 64-bit OS, and that's exactly the type of notepad that crashed, we need to do some adjustments. So the problem here, guys, is that we were using, when we queued this APC, we need to tell the system that this callback for normal routine, or the APC, is actually executing in a 32-bit process, okay? And that's important because otherwise it will try to queue the 64-bit code. In other words, it will try to queue this instead of this, okay? And that's the only reason why we need to do this little work here. And there is one undocumented API which is called PS-rep. No, actually, no, it is documented. Okay, that's nice. So Let me see if there is any, maybe they added it. Interesting. So let me see if there is any description, just real quick. And no, there is none. Yeah, it's just basically other people finding it. So maybe I'll write a blog post about it with my friend. We'll see. But basically what this function does, it needs to specify an address for the pointer to base address. It will just adjust it for us, and also it needs to specify our routine, and our routine is this thing here. And because we declared it as PK_normal_routine, we need to cast it here to p_void pointer, and that's all we need to do. Again, this API kind of like adjusts the let me just type it down instead of explaining it. Let's say instruct 64-bit version of NTDLL to use APC callback in the 32-bit NTDLL. That's pretty much all it does. Okay, so at this point we can build our driver. Okay, it builds all right. So now we just need to copy it, and again we take debug version and we need to copy it into our test environment. Let's remove this. Okay, well guys, let's start it again. Let's run 64-bit version of Notepad. As you see, it works fine. It created a line here, and well, let's do it again. Create it a second time, and again everything is fine. Let me delete this, and now the moment of truth. Let me start the 32-bit version, and it starts fine. As you can see, there is no problem here. And let me start process hacker. Let me go to the bottom of the list. Here's the notepad. Let me go into properties, and as you see, there is not only FAKE.DLL, this is also a FAKE.64DLL. Now that might be kind of interesting, because if you look, let's see, how can we tell? Does it tell you? Come on. Oh, this is a 32-bit image, as you see right here, as the process hacker is showing us. But I'm not sure if you guys were aware of this. Let's see, where's modules? Well, we can actually, we can inject a 64-bit DLL into our 32-bit process. I'm not sure if you knew that, but this is also possible. And the reason we can do this is because, well, we have very little dependencies here. So you see, if I go into our FAKE.DLL in process hacker, the only imports we have come from NTDLL, obviously no imports. By the way, this is a little bit of a bug here, it doesn't show ordinal one. Interesting. And also, let's see, it has, does it tell you about control flow guard? It doesn't, but that's fine. But this, you see how interesting, because it's NTDLL, and the way, again, the processes work on Windows, even 32-bit WoW processes, they also have to have some 64-bit DLLs, and usually it's NTDLL and kernel DLL. But if you look into anything else, like, well, like this DLL, for instance, if you look at imports, you see how much crap is in here? There's all kinds of modules that it imports from. Our DLL is very lean, because all it needs is NTDLL. So that's why we can inject it into pretty much anything. Okay, so at this point, as you can see, we can inject. And again, because we did it twice, you see the PID is the same. The only difference is the bitness of DLL. And for 64-bit, it gets injected only once. Okay, well, let's clear this out and unregister our driver. So guys, at this point we are pretty close to actually testing this on a full scale. So if we go into driver main, I'm sorry, not driver main, on OnLoadImage, we can release this little restriction here. If you remember, we basically limited it to notepad only. Well, at this point we can probably run it on the full system and also test it on a 32-bit operating system to see if it works there, because obviously, you know, it's not a given. And yeah, but we will do this next time. It will probably be a shorter video, but at this point our driver seems to be kind of full. I mean, not cool, kind of fully done. And it didn't take 15 videos to do that, but yeah, so we probably have a couple bugs and a couple inconsistencies here, and probably a lot of typos in my comments, but this is how you do this. Again, I'm going to stop this video because it's been an hour already, and in the next one we will do an interesting thing and actually test it on the entire system and test it on both 32-bit and 64-bit operating system. So thank you for watching and see you next time.